Organizing maps. I think, yeah, most of you know about it, but I try to go to these directions that maybe it's new for you, and I hope it's cool. So, in principle, self-organizing map is a very generic, but it's very interesting method that it's very astonishing in somehow, because in most of the applications that we were talking, for example, with clustering or classifications, or for example regressions or something like that, you always have some techniques or algorithms that are good for certain tasks. For example, you have linear regression, which is good for regression. Then you have PCA, which is good for transformation. You have k-means, which is good in principle for space transformation, or in general clustering or grouping. But as you will see, this simple method of self-organizing map, which was introduced in 1980s, and it has a background in 1970s from vector quantization method, it somehow covers all of them, and that's very interesting. So I think it's not the best in all of them, but it's always top 3 in all of these tasks. So if you learn this, it's most of the time is enough for most of the applications, that you can just solve a lot of problems with that. So you can think about this self-organizing map as a clustering method, as a kind of manifold learning method that I will explain. What does that mean? A kind of probability density model. And if you remember, we had these Gaussian mixture models. This is called the parametric models for this density learning. With some, you will see that you can train it in a way that you can treat it like a non-parametric probability distribution. So it has a lot of use for resampling or data generation and so on, if you want. And then obvious applications are dimensionality reductions, which is usually being compared with PCA or similar methods for visualizations and dimensionality reduction. And I will show you at the end that, for example, today, that it can be dimensionality reduction, at the same time it can be dimensionality somehow creation. It depends how to use it, and that's interesting. And then at the end I will finish with this similarity between SOM, and I think some of you know these ideas of topological data analysis, and for example these ideas from topology applied to data, like simplicial complexes, persistence diagram, and this kind of things. And this is kind of experimentary thing I did, and I will show you that how you can implement, and there are a lot of similarities as well there. So the basic idea of SOM is very simple. The idea is that you have a data, imagine this point in the space, and then for some reasons that we don't know yet, you just want to transform them to this lower dimension. For example, now I'm trying to start with the story of dimensionality reduction. So in principle, think about PCA. You learn these 2 new principal components. So it's independent of, in a way, it's independent of individual points. You learn this transformation in a global way, it's a geometric way, and then you multiply just your any data or vector in the high dimensional space, and there is a map to these lower dimensions. For example, if you take the 2 PCs, right? But in SOM, the idea is that you don't do it in a global transformation. It's similar to this DB scan, if you remember last week. That is a kind of topology-based approach. So in principle, you don't know how you're doing this transformation. It's not based on the ideas like what we had in PCA or similar methods, but it's based on topology preservation. And topology preservation means that you want to do it in a way, and actually this is the meaning of self-organizing map. I think it's wrong. Many people think that the final result is a map, but it's a mapping. It's a mapping from a high dimensional space to lower dimensional space. And the way you do it is a self-organizing mapping. So you don't know how this happens. In PCA is very clear. Here it's algorithmic, and it's a self-organizing map. The idea of topology preservation means that in this self-organizing mapping, we want to transform these data points to another space in a way that if 2 points in a high dimensional space, this can be pictures, this can be any data, this is your original data, if they are similar to each other or close to each other, if you visualize it, and this similarity as well, it can be based on any definition of similarity. Usually we take Euclidean distance. So if the points are similar to each other or close to each other in the high dimensional space, they should be placed in a lower dimensional space. So this is the whole idea. And if you can do it, then you don't know how this happens. So you don't have a closed form kind of operator, or you don't have a matrix of operator to say these transform my data to a lower dimensional space. but you do it in a self-organizing map. So if just reminder from last sessions that I already told you now, this is, we have in principle, in terms of transformation, think about it that we have a kind of geometric or global transformations, and then we have this idea of topological transformation, like DBS scan, if you remember. I don't know if you remember it or not. It was here on the last session. That, for example, in k-means as well is a kind of global, but in DBS scan, for example, if you remember, this was the idea. You try to look at the similarity of the data points. But there is another factor of importance, is data abstraction. In k-means, you do data abstraction. This means that you have your original data, and then, for example, in Gaussian mixture as well, you're just interested in the center of the your distribution. So this is a kind of data abstraction. It's not just the data itself. You learn, for example, the centers in k-means, right? But in majority of topological approaches, you don't do this data abstraction. So, for example, if you go to this field later and this dimensionality reduction, there are a lot of methods that they just learn how to visualize your high dimensional data, like t-SNE, LLE, a lot of them, isomap and so on. They're all topologically oriented, so it means that they just look at the distribution of the data and then try to learn this transformation in a way that the topology is being preserved. But there is no abstraction. So in principle, it's just a mapping from all the data points to all the data points. And because of that, most of the time it becomes very expensive. If you have millions of points, you need to find a way to calculate the distances of all the points to all the other points. And because of that, it's very slow. In self-organizing map, in a way, you want to be topological, but unlike the others, you have data abstraction. And the trick is that instead of directly transforming them, all the data points, you try to generate some kind of fictional, which are not part of your data, kind of capsules or nodes in your network that they are doing the transformation. So think about it like this, that, for example, you think about it like a grid of nodes or capsules, and this is a kind of what we call topology, and this is our decision to be like this. And then in principle, we think they're like a grid. And then this is your data points. And then we want to do it in a way that any of these points become part of these grids. And if this happens, as you will see, that this transformation like this will happen. Actually, think about this as a grid. Instead of having a two-dimensional continuous space, you have a grid in two dimensions. And this is the topology of the grid. This is the dimensionality. So let me see what I had here. These capsules are similar to the clusters in k-means, as I told you, but with the difference that they are also locally similar to each other. So now if you compare it with k-means, what we want to do here with this self-organizing map is that in k-means, this center of the clusters have no clue about the other centers, right? They don't know that there is some other. But here with some, we want to have another kind of correlations. So in principle, you have some kind of lateral and horizontal, like vertical and lateral similarity. So in principle, imagine like a k-means, but then you want to train them in a way that they talk to each other as well, the centers. So this is, I think you can, again, another way of talking about sum. But there are different interpretation. So the algorithm to go to this process is very simple. Let me tell you again if it's confusing. I don't know if it's confusing or not. So in principle, we have a grid, and this visualization, you should not think about it that the data is two dimensions and so. This is just, each point could be an n-dimensional vector. And this grid, in each point of this grid, you have a location in this topology, which is like an x and y. And then you have again an n-dimensional vector. So they try to mimic themselves to this space. Now think about it like this Gaussian thing. There we are trying to learn this center of these Gaussians in a way that they cover the space. Now here with some you are doing it in a way non-parametric, because you don't have a Gaussian assumption, but you just want to fit this space. And sometimes this is called manifold learning as well, because it's like a manifold in this high dimensional space, and then you want to learn this. And the moment you learn this, and then you have some kind of local smoothness, so it's a kind of you can do computation on top of that. So the idea, which was introduced by Kohonen in 1981, is very simple. Assume, and it's called online learning, which is easy to implement as well. It says, assume we have a grid, here a two-dimensional grid, and then each node in this grid has an n-dimensional vector, w, and a 2D index, which is x and y. So if you think about this dimensional reduction, this is x and y. So each node has two representational vector. Each node can be seen as a center of one clusters in k-means as well. So, but then you have another dimensional. So we initialize, like k-means example, we initialize these w's with random vectors, and then for several runs, literally, we do the following steps. Project one data point to this grid. So this grid is like random. So you just find, let me read it better, because then I forget if I write everything. Project each data point to the grid and find the most similar node using the selected similarity measure. So if your data points are graphs, then you cannot use Euclidean distance. There should be another method. You should devise it, or you should take another. But usually we assume that we have Euclidean space, so you can use Euclidean distance or any kind of LP norms. Then you just project one data point, and this is the projection, like this is one data point. And then you just find the most similar nodes to this data point. And then next, this is data point, this node is called best matching unit. Imagine it's like a kind of, this is the way Kohonen explained it. It's a kind of competition. These nodes are competing to each other to be the winner. And because of that, it's called best matching unit, which is the winner in this game. And then this BMU is becoming the center. BMU and its neighboring nodes adapt their weight vectors in a way that if next time the same data was projected, they become winner. So it's a kind of very greedy algorithm. This is called greedy because they say, okay, now greedy and myopic, because they say, now this guy was the winner, next time the data is like that for sure, because they are myopic, right? Then they say, let's mimic ourselves to the BMU, because next time if this happens, then we are the winner, or we have higher chance. But then next time the data is at different locations, then they run to another space. So it's a kind of, you can mimic it like a kind of particle swarm as well, that they are competing. And then you have adaptation. Adaptation means that they try to mimic themselves to the BMU. You just repeat these, and the learning parameters is the size of these adaptations. Like imagine if you assume that you have a BMU, and then this is the center, you have a kind of neighborhood function which affects the others. If it's very far, they don't bother to be similar. So you try to do this by a weight vector, which is usually kind of Gaussian neighborhood, and then by playing with the variations in these neighborhood functions, you adapt. If for example, if the variance is 0, this means that the BMU is not affecting anything. So you start with a large neighborhood function, a large radius, and then gradually you shrink this value. And then another one is the learning rate, that how all of them at the same time get will be changing. For example, they have the weight vectors, and again you say simply what is the difference, and then you just multiply this difference with the learning rate, and then you just change the weight vectors for all of them and multiply by the neighborhood function. So it's here. I don't want to go to it, but this is I try to write the functions like this. So you have random initializations. You simply take the minimum and maximum values of each dimensions from your data, and then you just start with a random value. And then you need to have a function to calculate these distances in this grid. And this is just once, because your grid has always the same topology. This in principle, it doesn't change. From the distance from each point in the grid to another point, this is x and y, is always fixed. You need to calculate it just once. And then you need to calculate this distance for the function, and this is the neighborhood functions. If you think about this, is a Gaussian function, and the distance, you do it for every node. Each node has a distance to all the others. So every time that it becomes the BMU, the other nodes get affected based on this weight. This is a Gaussian. It's very far. If you go very far, then the effect is very low. If you're very close, the effect is almost 1. Right? And then you have a function which is called find BMU. You just simply calculate the distance of the weight vectors of all of your nodes to your data set. And the key here is here. For example, if you had a kind of full topological approach, Then in principle, you had a matrix of here that the rows are the data points, the columns are the data points. You need to calculate all of them. And if you have million by 1 million, that becomes a problem. I mean, of course, you don't do it, but it's in general. But here with SOM, you always compare all of your data point with, for example, with 10,000 nodes. So this is the reason why it gets faster, for example. So then you just calculate the alpha rates of training, and then over time they decrease, and then you can play with that. And those are small things. So you just put what I explained to you, these functions to this loop, and then you run it, for example. You can check it. So this is the same data set that we played. It's useless, but it's a simple data set. It's a two-dimensional, and we don't know we have 3 clusters or 2 clusters, 5 clusters or 6, you know, because then we discussed that maybe it's a 6 hierarchical pattern or something like that. And as we did all of the examples with k-means or dbscan, this was the data set. So now I'm going to do this. I don't run it here because it might take few seconds, but yeah. So in principle, I say do this loop for 400 times, and then the size of the map is 40 by 40. So I have a network of 40 by 40. So I have 1,600 nodes, and each of them has, in this case, like 2 dimensions, right? It's clear. So you train it, and then let's train it if you like. It's not that slow. So this is happening, and this is, you have a measure for your success, and this is quantization error. Quantization error simply is the average of your dissimilarity to the BMUs. So you expect that every time that you're running, in every time steps, the quantization error is decreasing because you're becoming more and more similar to your data. And you can visually see it here, right? When it's like that, so your weight vectors are very similar. So your quantization error should go down. And then if you visualize the quantization error, you see that in the beginning, because it was random, it has a very drastic change. But gradually, after some fluctuations, it goes down, and still is not converged, but I stop here. Because if you continue, you see that the slope is very high, so it might continue as well. So if I visualize these things for you, all the steps, now what I do is that, again, it's a bit misleading. Think about it that you always not your data is 2-dimensional, but here we are mixing both data and the dimensions of the SOMs are 2. Think about it that if you're using SOM for images, so each pixel is your dimensions. If you have 100 by 100, your dimension is 10,000, right? It's not 2. But here the data is 2, and then the dimension of the SOM is 2. And this is the way you start. The green points are your SOM nodes, and the values here, but I don't show here at the first step the grid, which means that the connectivity. So they're distributed all over the data space, and this is your data. And gradually, you see, after just one run, this is one, and the second, after maybe like one step, it already gets the idea. After the first data point, like, right? It's not. I think it's not correct. It's not just one iteration. There are several. But then gradually you see they're trying to compete and adapt themselves. And if you wait, they try to get the shape of the data, right? So in principle, you expect that around these centers you have a more density of your nodes, and then in between they are trying to keep some kind of smoothness. So in principle, they try to fill the space, but because here is very unlikely that some data happens, so it's very empty as well. But you have this, I mean, if you increase if you play with your training elements, you can make it overfit, but this is not good.
This is what I was gonna ask. That you reach a point of overfitting if you iterate too much.
In principle, yes, but because of this topology that you have, I will finish today with this, that you can think about each of these nodes as a dynamical system, that in one step, if for example these poor guys here, these guys are in between west and east, so every iteration they go to the east or west depending on your data point. So if you think about these points, they're always fluctuating. If you think about these points, they get very, very converged. And I think because of this topological problem, for example, if you do it with k-means, it becomes the case of overfitting. But here, this guy is connected to this side and this side, right? So in principle, you cannot overfit with some. That's another thing, right? Because at the end you have some data, some of the nodes in between. But for example, with the other methods, like you will see, like for example, decision trees, they get overfit. This is possible. But here, it's very unlikely. But definitely, if you increase the size of the iteration times, and then you play with the radius and learning rates, it is likely that here it will be vanished, right?
And the problem of overfitting is that you don't have information in between.
Overfitting problem is that the question is that you should not trust 100% your training data, because in your training data there is no observation here. But when you do the generalization, proper generalization would be to say, with lower probability, this is possible that next time there is some data. If you do if you have overfitting problem, next time that you have a data point here, you have no information. So this is the thing. This is the problem of overfitting, and this is happening, for example, for neural networks, regression models, decision trees, and then you need a lot of data, and So this is called online learning. It's very simple, right? You just project one data point, you adapt, you find the best matching unit, you adapt all the others, you do it, and then you just shrink and change the size of the learning rate and the radius, and over time. It's not proved, but empirically it's been shown that it's converged. There is no proof here, unlike, for example, PCA, that it finds this orthogonal patterns and so on. But then there is another way of implementing this algorithm, which is called batch learning. And this is kind of modification. The problem with online learning is that imagine if you have 1 million data points, you cannot parallelize it, because in every time step you need to wait for the next data point, right? So you cannot parallelize it. So you can parallelize the calculations of the distances, but you cannot parallelize the data projection. There is another method which is called batch training. It's with some modifications. I can tell you if you like, but I think it's not that important. Instead of projecting one point, you project all of them. And then instead of adapting for each data point, you adapt them based on a weighted function. You can, yeah, that's it. And I did some... I don't want, because I have a lot of things to say today, but I can give you, my code, for example, this code is, I wrote it during my PhD. This is now open source in Python. This is batch training, and then in principle it uses parallel cores in your CPU and so on. It's much faster. But I didn't prepare. If you insist, at the end I can show you how it works. It's very simple. You just need to adapt the weight vectors based on a weighted effects that you could get if you had this online training one by one. So you have, imagine in every, like each node is going to change every time it steps. Then you need to know the BMU, and then you need to know the distance to the BMU, so you know the weights that you're going to change. So you just, when you do the batch training, you take the BMUs for all of them, and then you say, okay, for each node, what is the distance of this node to all the other BMUs in this batch? And then you do the adaptation at once. Because you say, for example, node number 2, it has connected to all the other nodes in principle, but then instead of doing it for all the other nodes, you just say, in this batch of the data, give me the BMUs. So, for example, if your batch is 100, you have, in principle, maximum 100 nodes, which are BMUs, right? So you just calculate the distance of each node to all of these 100 BMUs, and then so you have the weights in the adaptation phase, and then you know the amount of change that you are going to do. And you can write it down like at a simple weighted average, and it works. So this is much faster. Yeah, trust me, it's okay. So if you do it like that with the same data now, it's not that fast apparently. So it's 40 by 40. I think something is wrong. So it's done, I guess. Yeah. Now, this is the way you got. Like this is the same thing, right? From now on I will work on this, and you see it's not that different. It more or less has the same pattern. So what I forgot to tell you about this. In principle, what I thought would be more helpful, I think, in this session, in this weeks, I think it's better to talk about functions of these algorithms. I mean, because if you want to talk about how this algorithm is being converged and so on, this becomes more like a computer science course in machine learning. But I mean, opposite to that would be to think about this sum and trust the algorithm, and you can implement it, of course, and then think about it that what is this good for example, what are the functions of this. So in most of these sessions that I have, in principle, I try to always briefly say what is the algorithm. I don't want to be confusing, because of that I'm just trying to skip it quickly, but I want to say, okay, what is this good for in principle. So if we talk about sum and applications of the sum, for example, there are a lot, for example, of applications. For example, dimensionality reduction and visualizations of high-dimensional data spaces. This is obvious, and for example, you will see this in a moment. You want to create a kind of atlas, or just kind of you want to create a spectrum of possible patterns. For example, what I did for like these cities and so on. You can take a lot of pictures, and you want to just visualize them in a map, which is like a nice pattern. So this is very easy to do it, right? Because then you have in this two-dimensional grid, and then you can think about sum in that way as a kind of multi-dimensional sorting. You will see this in a second. And then you can use it because of its visualization power. Think about it that here, for example, maybe I should skip this part and show you the result. I will just read it here. You can use it for multi-criteria optimization and design space exploration if you want to know what is happening in the space of your objectives. If you have more than 5 dimensions, usually cannot visualize it. Like if you have X, Y, Z plus size and color, but then you have 6, usually don't know what happened. I show you an example here. And you can use this for feature selection. There is a very interesting way of using self-organizing map to tell you which dimension has, for example, no effect in your data. For example, if you care about this, if your experiments are expensive, you can remove them. But usually, for example, for function approximation, it's not a point. And then, as I will show you, there are different ways to use sum for clustering. Then you can use it for classification. Again, I will show you at least two ways to use it for classification. And definitely it's comparable to PCA and k-means and sparse coding. And in that sense, this would be the connections to sum and the way that in deep learning system works, that it's not any longer dimensionality reductions, whereas each node of the sum is one dimension for itself. I will show you this example as well. And then function approximation, this is obvious applications, and it's very powerful. And then transfer functions is another story. Non-parametric probability density estimation. These are the applications that I personally have been involved and I've done. And I think it's very easy to use sum for all of them. For example, I told you it's very similar to Gaussian mixture model, but it's non-parametric. And then, for example, you can use these for resampling. And then you can use it for missing values, filling. You have these are very challenging problems in practice if you want to play with the data. Usually the data is not complete, so you can use sum. I can show you how to fill your data, because in principle it learns this dimensionality, this probability space. So if one of your data points has missing dimensions, you can estimate easily based on these learned patterns. And then data abstraction, and this is similar to topological data analysis. So first thing that you can do with the sum, simple thing, this is called a heat map. And then this is the distribution of your data in this two-dimensional space. Think about it here, your data is two-dimensional. Because of that you can visualize it, but if your data has 100 dimension, you cannot visualize it, right? But here it tells you what is the distribution of the data in this space. And think about it like what we were talking about here. You have a higher dimensional space and you want to transform it to a lower dimensional space. You project all of your data points to the sum nodes, and then it tells you what is the distribution of the data point. For example, here the size shows the number of data points attached to this area. So this is very simple. You can use it very fantastically for resampling, for example. You can, by random, select a point in this space and then look at the data inside. Because each node, in principle, is representing a group of data points. Then you can think about it locally, you have a histogram of your data set. So it's a kind of dynamic table in principle. So you can use it for example, for data generations, or if you want to do estimations, you can by random, for example, select one point here, and this point is a kind of node, and this node has been BMU several times. So if you keep these records of your data points that belong to this point, you can do some kind of locally linear estimation, for example, in that space. Another key term is, for example, component planes. Now, in your case, you have 2 dimensions, so in principle, I can visualize them like a map. And this is the, I think, misunderstanding that people usually use SOM for, and they call it map because this is a kind of map, for example, but because now in any of them, that's these dimensions, I have one map. So if you have 1 dimension variable 1, variable 2, I visualize them like this, and in principle, if you can read this map, you should be able to tell me that, for example, here we have 3, for example, 4 main clusters. Look, this is one cluster when the variable 1 is red, which means that's a very high value, and then you have this, which is the variable 2. You see it as a pattern, and then you have another pattern which is here, and then it's here. And then you have a larger area which is like this, and it's a kind of mixture. And you can think about it if you want to visualize, but you should not do it. One is talking about this, one is talking about this, and one is talking about this area. And because of that, this area is again has some kind of substructures, right? So this is the very, very common way to use SOM for a lot of fields of applications. For example, you have a lot of observations, and then you want to know if there is a kind of non-linear pattern, because as you will see immediately, in many applications you cannot find linear correlations, whereas there are some local patterns. For example, this data set that you have here is a data from meta parameters of a very expensive simulation in computational fluid dynamics. So in principle, our simulator has like 5 factors. And then in order to do all these combinations, you need to say, for example, for P1, I take lower value, mid value, and upper value. And then you have a kind of combinatorial problem, because if you have 5 variables, you have 3 to the 0.5 experiments. And if any of these observations or tests takes like 10 minutes, that's a lot of time. So this was a case in wind flow, I think, simulation based on CFD. And the idea was that, can we say which of these parameters are helpful? For example, the idea was that to set up a test and then tell you that at the end this result is good or not. For example, you have a label. But then you don't know how this space is changing regarding to the label. And then if you have a lot of tests, you don't know is it good or bad, but it takes a lot of time. So here the idea is that using this kind of visualization, can we identify which factors are good, for example. And if you look at the data, it's like this. This is one experiment and the label is 1, and some of them are 0, right? So if you go to the classical way, and I say label 1 is, for example, blue, label 0 is red, for example. So this is the relationship between P1 and P2. This is the way you sample your data and then do the test for each of them.
P1, P1.
Pardon? P1 is meaningless, but I just do it because it's diagonal. That's right. P1, P2, P1, P2, and actually they're like overlays, right? This is a kind of projection, and some of them are 0, some of them are like, for example, this one is red, but you cannot really understand what's going on here, right, in this space.
What does it mean when it becomes red?
This is the label. If the label, for example, is 1, this means that your test is correct. If your label is 0, for example, is red, or the other way around. But the idea is that, for example, can we say, okay, what's going on? Can I remove, for example, factor 2? Because if you add one factor, the demand for a computation is increasing exponentially, right? But if you use these classical ways of models, it doesn't work. Even if you do the correlation analysis, you see there is no that much of correlation between this dimension, or there is no correlation between any of them to the label. This is important, for example. If you want to literally say, okay, this is one dimension of my experiment, this is another one, and I want to know which one I should add or remove. Because adding one means that you need you need to have 3 times more experiments, because each of them has like minimum, maximum, and the medium in the middle value, right? So this is a very technical problem. You need to reduce your time. And if you do this kind of scatter plot as well, it's boring. It doesn't show you anything again. There is no correlation that much. But I just really did this like few years ago, and they just train a sum in order to see the patterns. And then now you get something like this, right? You have 5 dimensions, each of these parameters, and then I train a sum with 5 dimensions. And the problem here was that we cannot visualize a 5-dimensional space. We only have 2 or 3, and it's becoming complicated. And when we did this, it was funny, because then, for example, if you look at this, the values are 0 and 1, and then we are looking to see if there are some holes or clusters that they're determining the results. And for example, you see that here the value is not changing, but the results of the experiment is changing. So in principle, you cannot say this dimension is that helpful. For example, when the value of the parameter 1 is very high, which is red, you have either both 0 and 1. So in principle, it's not that informative. And here as well, you have locally, for example, when it's very low, it means that it's 0, that's right, but again here you have some kind of patterns. And then if you look at all of them, this is a very quick way to remove data. And this is a very toy example. I have, for example, like, maybe 10 years ago, there were some examples that in complex manufacturing systems, like steel making or like this kind of patterns, you have like 8,000 factors, and you want to know which one is affecting to your final results, because, for example, you're looking for a specific kind of steel, and you don't know which one is good, and you don't know should you observe all of them or not.
Okay, so here you run the sum independently for each one of the factors.
No, you just run for all of them, but you take out the labels, but you just visualize the label. And actually we did this with a group at a future cities laboratory, and they were so always complaining.
This is for the topics of the researchers.
No, this is just CFD.
Okay.
Yeah, this is CFD. But as you see, there are not clear pattern, but just shockingly, look at this dimension. This is somehow determining the final combinations, right? And for example, think about it, that now with this simple visualization, now you can unfold this complex pattern, and then look when the values are very low, except this part, I think maybe there's an error.
It's right.
But usually this is determining the final result. So in principle, what we told these guys, who are engineers, is that these values are not necessarily helpful. You can just play with these dimensions, and you can increase the quality of your test by adding more values to these dimensions, and the others are somehow arbitrary. And as well, you can learn it, or you can select random values over there. Because if you visualize it in a classical way, which is the classical statistics, you get something like this, and it's super confusing. But with simple visualization, you see that these dimensions is really dictating the final results. And it's nonlinear, because when you calculate the correlation of the factor 4 is 22%.
Can I ask you?
Yeah, sure.
Why a PCA would fail to do exactly the same thing?
PCA might be helpful, but the problem is that with PCA, you have the latent dimensions, and with the latent dimensions, you cannot. You need to come back again, because your experimental setup is not based on latent dimensions.
Mm-hmm.
I think if you get good results with PCA, but it doesn't tell you exactly which factor is 100%. Okay. Or maybe it works, but I think it doesn't work. We can try it with PCA, I think. But I think it's not working. So this was a very basic application. Then in principle, you don't need to use k-means. If you use with sum, you already have k-means. So you can use SOM for clustering. If you reduce the number of nodes, for example, to 4, this is similar to k-means, right? If you increase the number of SOM, you can think about it that you have kind of a smoothing on your data because they are locally sampling the data, and then you can upload, use on top of that, use k-means. And this is a better way usually than using directly k-means. So you have a data, instead of using k-means, if you want to cluster your data, you train it with SOM. SOM is doing some kind of smoothing, local smoothing, and then you train k-means on top of that. So for example, in this case, with the same data set, if you train it, you train a SOM, you can train, for example, clustering on top of that. You need to select again what's the number of clusters, right? So if you visualize it, I get the same result, right? I do just clustering on top of the nodes, and then each node is representing the data points. You don't need to do the clustering on the data points. So in principle, from the point of engineering again or optimization, this is faster because SOM is faster. So, but usually there, this is what I'm just quickly telling you. There are like a lot of people working in any of these tasks. For example, I know like at least 2 persons worked on this clustering of SOM for their PhD, but now it's like after 20 years it's obvious, and then you can easily use it. But I think it's just good to know the techniques. And then there is another method called U matrix, for example, and the guy who developed this, his name is Alfred Ulsch. And he come up with this idea that how we can get rid of the number of clusters as a meta parameter. Can we find the clusters in a so-called natural way? So what we do here is that we think about this space of the SOM, like this heat map that I showed you. But then on top of this trained SOM, you go and just check the similarity of these weight vectors to all the neighbors. So each point, you just calculate what is the average similarity of this point to its neighbors. The idea is that if you have this kind of sharp edges, this will be identified because there are some areas that suddenly they're very dissimilar to each other, and because of that you create kind of landscape. And then Alfred Ulsch shows this in many papers, that this is called emergent SOM. If you increase the number of your nodes, you can invert the clusters on top of that, for example. And we do it here quickly as well. So you have this, and then if I just calculate the average distance of each node to all the neighbors. So you can say the first neighbor and second neighbor, first neighbor and third. These are again like meta parameters. Here I just say calculate the U matrix. The distance is 2. It means that it looks at the first and second level neighbors and then just sum the values. And then when you do that, it creates this pattern. So it's obvious, right? It's kind of edge detection. And then by that you see that it learns the clusters in a way that there are like one main cluster, and then there's one main cluster, and then it has like 3 sub clusters. So you can use this in a nice way. For example, I developed an algorithm to automatically detect these edges based on some image processing. But then what is your benefit here is that you just say, I don't care about the levels of hierarchy, I don't care about the number of clusters, it's being immersed. And because of that, it's called emergent SOM. And actually it's very helpful, I mean, in many applications.
It seems that there's if we use this method, it seems that some data point are not belongs to any clusters.
Yes, this is possible. Yeah, that's possible. Yeah. This is like in when you have this kind of outliers, for example. These are the points exactly that they are actually. This is the border, for example, right? And if you increase the size, but as we discussed last week, I think clustering, if you want to cut the space, in principle, is not, I think, encouraged, I would say.
Which is your favorite method for clustering?
This U matrix is usually the best. Yeah, this is usually better. But my favorite thing is not to do the clustering. I mean, if possible, don't do clustering because you cut the space. Yeah. So what's the point? As we discussed before, for example, if you use this data with k-means, doesn't work, right? Then we have this topological method. So if this SOM is topology preserving, so it should handle this one. So I trained here a quick SOM, and for example, I expect to have here like 4 clusters, but you see that k-means doesn't work. If you implement k-means on top of sum, this is what you get. But if you calculate the U matrix, it gives you this. So these are the tricks, right? Because of that, this U matrix is interesting in principle. So if your data is like this, that's not a problem. It finds it. And you will see at the end, I will show you this is a lot to do with topology, and then in principle this fields of topological data analysis. And this sum is a very good way to learn the shape of the data. This means that clusters, relationship between these clusters, and so on. So you see that k-means fails. I mean, we saw it last week as well, but this simple U matrix, which is a very simple idea. As well, you can think about the density vector as well. This could be another factor. Not just the similarity, but the density, because clusters are those areas that have higher density. So you can combine this, for example, similarity with this heat map that I showed you here. Then you can assume that those areas with higher density, they are the center of the clusters. And there's another method which is called, for example, U star matrix, which is a combination of these together, and it works better than this. But I think U matrix is enough. So in principle, this was like with clustering. I mean, it's very good for clustering. And then the interesting point is that you can use it as well for classification, right? And how you do it is that you look at the local distribution. Like imagine, your data has a lot of labels. The easiest way and common way is that you don't use the label as a part of the training data, and then you just train a sum. And then when you are projecting a new data set, you want to know the label, and this is the problem of classification, you just find a BMU, and then, or maybe you can say I want to find 5 BMUs, which are the most similar, and then you can just look at the data that belong to these 5 BMUs. So you have a kind of local histogram, right? And then if you are caring about the labels, most likely if your data is correct, I mean, there are some causal relationship or correlation between your X and Y, you can vote internally. You just say, okay, now my new data set is projected to this area of the sum, and then this area of the sum I have these 50 examples, and then you just look at the labels. And I have done this, for example, for binary classification with time series, and it's very good. And many other applications it works. You just go to the inside of the sum. You just don't use the weight vectors. Usually we use the weight vector of the sum, but here you just want to go inside. And then inside you have a kind of local distribution, and then you can do a voting there, for example. And another way that it's not usual, but it's again very interesting to do, is for classification, is to think about as the whole sum as an activation. For example, now think about it that if you train the 2 sums, if you have binary classification, 1 sum with the data with the label 1, 1 sum with the label data 0. So when you project a new data point, you don't know the labels, you have a kind of activation. But don't look at the BMU, just look at the whole activations. So if you have kind of deformation in your data, for example, in 0, for example, one is about digit 0, one is about digit 1, and you have a lot of deformation, but overall they are more similar to the data point. So in principle, you have a higher activation than the other one. That one that gets a higher activation is most likely to be correct. So it's a kind of collaborative classification where it's not a dimensional reduction any longer, it's kind of new dimensionality, that each node is a new dimensionality. I will show you if it's confusing. So just before that is regression, this beautiful regression that we did with polynomial regression, and I showed you this diagram. Now imagine you have this data set, this is what you get with regression, because it should be a line. So you train and learn the parameters of the line. But you can do it again with sum. And now imagine sum is in principle unsupervised, but you can use it in a supervised way. You train it with X and Y, and then you project a new data only with X, and then you just say, tell me what would be the most likely Y. And then I do it here, and then this is what you get. So it learns the relationship between X and Y very nicely, but it's not a function. So it's a different word, right? This is what we discussed a lot before. So you can use this in a lot of applications, right? For example, what Muhammad, for example, did is his PhD, this very beautiful way of emulating water flow, is somehow it has these things inside it. So if you learn this as like blocks, you will see that it works in many applications. But it's not just the final solution for a ready questions, right? You need to learn this, and it's very generic, and you need to play with that. And if you learn to play with that, you will see that, wow, I'm playing with, I don't know, Bitcoin data, I have this binary classification, let's try this. I am playing with, I don't know, image analysis, let's try it. I'm playing with this robotic problem, you need to move, like for example, the robot's arm. This is again kind of function approximation problem. There are a lot of that. So it's very generic. So as I told you, you can now think about it as a kind of transformation as well. And this is what we do in PCA, and this is what we do in topology preservation methods, right? And in SOM is like that. So in that sense, usually it's considered as a dimensional reduction method. However, in addition to dimensional reduction method, SOM has data abstraction that we discussed. And in that sense, similar to PCA, sparse coding and k-means, with large K, each node of SOM can be seen as a new dimension. So you can think about it as a dimensional reduction if you want to visualize this 2D. But if you think about each node of the SOM as a new dimension, like what we did with PCA or k-means, now think about that when you have a new data set, you can just calculate this dot product of your data point with all of these weight vectors. So it creates a kind of activation. And dot product means that if you have like two vectors which are aligned, dot product is 1. So they're very similar. If it's orthogonal, it's 0. So when you multiply your data points to all of these weight vectors, you get an activation. The values are between 0 and 1. So if certain region is dealing with labels of, for example, 4 or 1, then that area gets activated. So you can think about it as a new dimensionality. You can think about that the result of a SOM as one picture. So this image, when it's activated in a certain way, you can say this is digit 4 or this is this pattern, right? So we do it here with this MNIST data, and this is the data we have. I think you know it already. So I train a SOM with 50 by 50. This is the usual way of visualizing. If you think about visualization or dimensional reduction, this is the values of the SOM, right? You remember this, we did this with k-means as well and PCA, and k-means is similar to SOM, but PCA, each principal component doesn't have the whole digits. It's just one aspect of the digit. Whereas here, each node of the SOM is somehow talking about the probability space of these digits. So in principle here, you see it's how it's morphing from 2 to 8 to 9 and so on. So if you think about visualization, this is visualization. This is the very common use of SOM. But think about this as dimensionality. So in principle, now I have a new data set. For example, this is my test data, and now all of them have label 1. So another way to think about SOM is, and this is very similar to what happens in deep learning, you will see that this later. Now I project any of this data point to all of SOM, and then I get this activation. So I expect that if this SOM has learned all of these deformations and this orientation, the labels 1 should have the same activation. And this is happening actually. So this is when I have label 1. For example, I have 9 data points, and think about that each of them being multiplied with these weight vectors, right? And then get a value. So you see they have created more or less the same pattern. The same areas are activated, and for this one, for example, is a bit different, but you see still the structure is the same. So if you think about a kind of classification, you can say that now SOM itself is just one step of data transformation. Now you can take this as your data to train for another classification, for example. You can take this for linear regression, for example. Because now with this new dimensionality, you are somehow captured invariances. Because they are activated, but you see the data is somehow changing, but because they have been shared this information together, they get overall same pattern. And for example, let's see if we do it, for example, this is like, if I do it with this, for example, I expect that the label should be this. So this is 4, for example. Now I do the same thing. Oops. Okay. Thank you. What happened? Cannot reshape. Okay, I think we should train it. But did I train it or not? No. Sorry, I need to. I hope. Okay, escape this part because the plotting of this takes time.
No, the range is wrong.
The range is wrong.
It's 5,000 to 5,009.
That's okay. No, this is okay. No, I think the data. I think the sum was not trained, so I think it's using another sum. I hope. Yeah. So you see, this is 4 now. So we are abstracting from any point. Previously, usually the usual way of using sum is to say find the BMUs or 5 most similar points. Like for example, if it's 4, where is 4? For example, you might say here is the 4. I cannot find it here. For example, these are the most values, and then you say tell me what are the labels, right? But here what we are using with this activation is that we are saying, okay, this area tells me that for sure it's not, for example, 9 as well. This is the kind of information as well, right? So I use sum not as a dimensionality reduction, but maybe you can increase your dimensionality as well. And this is, you will see that in deep learning, this is the whole idea, that you add these layers, and each layer is being like a kind of transformation in a way that similar patterns have similar kind of activation in different layers. But here is just one layer and it's unsupervised, whereas in, for example, most of neural networks, this is kind of supervised. You train it in a way that you dictate the model that similar patterns with the similar labels, they should go to the same channel. And I think this is very fantastic result. Look how similar they are.
So in the sense, if you have already trained your data, then probably you'd retrain it, rethrow every event, every data point.
You can do it.
And then vectorize it again in terms of the activation of the whole.
Exactly, yeah. Because this is just like, for example, our sum is, for example, 50 by 50, and your data is 20 by 20, right? So you moved it to a larger space, and then they are like a spread. Like
yeah, it's a complete, and also generative.
Yeah.
It's not just like kind of classifying what you gave it, but it's inventing new.
Yeah, yeah, of course, of course.
In the spectrum.
Exactly, it learns all the possibilities. So, I think. But then, for example, you can do it for your test data as well, right? You just need to keep the dimensionality. Because what is important is that you have a matrix now. Think about your sum now as a matrix. If you have 50 by 50, you have 2,500 by the dimension is, for example, 700 dimensions, right? And you just multiply this, and it's super fast, and then it gives you an activation. And then now you can think about this activation as a way of representation. So this is the point that you cannot say sum is for dimensionality reduction or not, right? And I think I've never tried this in a real application, but I think it should be cool. I mean, if you find some application. And this is not in the literature as well. Usually nobody's doing that. So, and also, as I told you, you can do it for each class as well. Because the problem is that when you do it for all the classes, you have less space for each classes, right? You just say this area for 0, this area. But what if I just train one sum for label 1, one for label 2, and so on? But the problem, you might expect that if you have 1,000 labels, you need 1,000 sums, right? But with binary classification, I have done this before, and it gives you good results, very good results. For example, like we were doing some kind of financial time series prediction, which is you just want to say it's going up or now. So you have a kind of representation. That time was not the time series, but you have think about like wavelet on top of the time series. So you have some patterns like this, but because of the randomness in the market, they are going fluctuating, right? This is similar to these values of different zeros. You see, you have different orientation and different angles, and you do the same thing for ones. And I didn't expect that this is one. It trains all of them. So in principle, this is the direction that you can compete with, for example, what you ask about, like convolutional neural networks, because here, and I think here is, in my opinion, what is very guess, I would say, I'm not sure, is this is very similar to this capsule nets, because they learn together all the equivariances, not equivariances, but they learn all the deformations, and maybe if you can combine them together, this is the case in deep learning.
But this is your data set, which you have.
This is the sum. No,
But
these are the visualizations of the weight vectors. This is
yeah,
an
it's a
abstraction
sum
from the
with-
data.
I mean, all these points, all these nodes there, they represent a certain data point that was already in your data set.
Yeah, sure.
Yeah.
No. This is just visualization of the weight vector. It's not the
It's the
data.
weight vector.
Yeah. You know, for example, in your case, that
But
you're
it's generated.
because you are working with the graphs, and you, for example, you are using the median sum. You don't have a vector representation for the
Yeah.
nodes. That's a problem. Then you need to take randomly one of your data. For example, I do this for maps of the cities, and then because I'm using a dense vector representation based on this deep learning methods, this dense vector is not a map. It's just a 200-dimensional vector. But here, the data is directly there, so it's just visualization, right? Here and here, you see it's super confused because it's in between two patterns, right?
But
And
in
then-
this case, the sum is bigger than the sample, so
No,
of numbers.
I don't know. Maybe.
Because then
It
it's
doesn't-
kind of oversampled to create these numbers in between.
No, it's not. It's not. Yeah, in principle, if you increase the number of nodes, you learn it's in between. But if your data are similar as well, they
Then
become clustered in
okay.
center node, and then again it learns in
Yeah.
between. That's not a problem. But usually, if you have more data, you need a larger sum. And then I just simply do like this. So I have a new data set which has the label 1, and then I want to give the activation. I multiply these product, and then I visualize the activations, right? So if, and then each of them are like one data point. The red is activation of, this is 1 and this is 0. And as I expected, when I multiply just that product, you see the red's values are always higher as a distribution, right? And then you can say, as a kind of classification, you can say, I think all of my experts, all of these points, they all together agree that this is red, for example. And this is a different way of using of sum. In fact, it's not based on what we call K and N, which means that you select only the top similar points. Here you just select all of them, and then you see the activation is always better. And it's a kind of distribution, you see. But it's kind of superior. I think you can say that red is dominant. So if it's a classification problem, you just say, no, it's very good kind of classification. But in any data set that you have, you need to test it with real data and then apply it. But I think for binary classification, this is a very good approach without this kind of convolution or something like that. So there are a lot of modifications over the last 40 years. Yeah, maybe more. On some, for example, you can play with the topology. All of these topologies that we talked so far was like grid. So it's like 2 dimension. You can make it 1 dimension, but it still is a grid. Like if you say the grid is linear vector. But it could be spherical. It could be like a cylinder. It could be like a torus shape, right? These are different.
Luca was doing this. You saw he showed you this 3-dimensional representation of the sum with this triangulation. And
Yeah, you can do it exactly like that as well. But this is when, for example, you don't have any fixed topology, for example. There is another method called neural gas, which is exactly is doing that. So in principle, you just say, relax these assumptions that they are bound together by this grid. Because this grid is kind of a meta parameter. And if you relax it, and if you don't care about the visualization, the pattern will emerge. And I will show you this. And this is the last part. And then you have this idea that, for example, we can have a growing self-organizing map. We start with 2 nodes, and then if they are not enough, expand. And if they are redundant, remove.
you don't need to preset the number of cells.
Yeah, it's possible.
Ah, cool.
And then you have hierarchical sums, for example. And these are very old methods, but I think nobody's now going to them because they're not hot topic, but I think this hierarchical sum could be similar to what we have in neural networks, because then you have the notion of layers, and then you have growing hierarchical sums, and there are all applications implemented, and then you have neural gas, you have generative topographic maps, and then you can play a lot with the similarity measures. For example, you have this notion of relational sum or median sum. For example, this is what Manos is doing. When you cannot represent your data directly with a vector, for example, if you have graphs, you need to replace this your similarity measures with a kernel function. So this kernel, for example, can compare two graphs, but then the nodes in the middle, you don't have a representation for the nodes. So you need to take the median value, median data points from that data set that belong to that node. This is called median sum, and there are a lot of that. And then you have vector-based sum, non-vectorial-based sum, and so on. And the last part that I think this is interesting in terms of what we have in topology and the fields of almost recent field of topological data analysis is that now I would say you can start with this neural gas, or even without. I tested this with any topology. Let's say with a grid, but then when you want to visualize the result, don't think about this 2D space, because in topology you care about the shape of the data. You want to do a cluster. So you can think about them like a graph. And then you just say, I forget about this fixed grid, which is a kind of a fixed boundary. Just say, I define a threshold, and I calculate the similarity of each node to all the other nodes. And I say if two nodes are similar, and then I normalize the similarity. If I say this normalized value is between 0 and 1. So if I say it's more than 99% similarity, then there's an edge. If there is none, no edge, right? So I can play with this threshold, and you will see what happens. And this is a function, for example, we do here. And for example, let's see. So this is a sum based on, again, initial data that we had, this famous useless data. This visual, this one. So so if I train this, and then now I do this procedure, forget about the topology, and you just want to know the so-called shape of the data. And I calculate these topologies, this graph in fact, and without no triangulations, just they're connected if they're dissimilar. And then it creates these very interesting patterns. If you take 99%, so it's kind of mess, and then if you decrease this value of threshold, they gradually emerge. And this is what we do, for example, in topology, because, for example, you can over time you can study these patterns. For example, it tells you that here is kind of mess, but gradually when you change this over time, this threshold, you see that these three main patterns are emerged. And then at the end, when you have the value of, for example, 70, this is the most stable one. So in topological data analysis, because it's based on the data, you change this threshold over time, but and you look at the consistent features. For example, you can count how many connected area we have, and then this is very similar to what we have in topology in terms of like Betti numbers or like Euler characteristics and so on. And then we have these ideas like in simplicial complexes and so on. Is the same in a data-driven way. You need to change some threshold. Like if you want to make these simplicial complexes, then the question is what should be the radius of this connectivity, right? Then you have these circles.
And somehow here
it's the same.
It's capturing the distance, the topological distance.
Exactly.
Between the
you
nodes.
look at the topological invariances.
Because with the grid, you always have somehow a fixed, and then you have to calculate it after the
exactly.
and so on. But
here you just want to know, regardless of that grid, what is somehow invariance. You see, this is not acceptable that much, but after a while, when you change the threshold, it says, look, for example, here you have like 1, 2 again, and you see this is exactly your data points. You remember the style of the data, and then it's changing. But if you just calculate these topological features like number of connected points and so on, this has become very stable. So what is invariance is these shape-related factors. And this is what, for example, people call shape of the data, for example. Right? And this the last, I didn't expect that, I thought that this will be very converged, but it's very funny because here, after a certain threshold, it again gets a very good form. So now for this data set, if you do it, it tells you this pattern. So you see, it's the whole idea that the algorithm should be topology preserving.
It persisted, huh?
After a while, it persisted.
But the edges are like, it goes like a radius, huh? The edges.
What do you
that
mean?
it created. And there's like a little shadow inside. Those are the edges, right?
No, the idea. No, the problem is that actually we don't need it. But here I just still connect the similar, the original
but
grids.
you're tracing edges there. I see something.
Yes, because I try to show you as well the original grids, but it's useless in
But
principle.
it's still a 2D grid, actually.
Yeah. No, here I think it's 1D, for example.
Okay.
Doesn't matter.
Yeah.
Even now, the beautiful thing is that if you now you can relax the assumptions of 1D or 2D, it could be 100-dimensional grids. That's another problem. But then you need, you see what I mean? It's like you don't need to forget about this 2-dimensional or whatever grid. It's a graph, and graph is a dimensionless space, right? You don't have it's topological, and you see that this is learning these topological patterns. And of course these are obvious, but then for example you can do it, for example, in many applications. There is a company with a startup of Stanford, I study, and they did, I think, interesting works. They don't use SOM, and they develop their own algorithms, but in my opinion SOM, you can do it with SOM as well. So they do a lot of things with different disease or different things, for example, detect fraud, and because they are looking for the shape of the data. And in that sense, it goes too much to kind of data clustering, because they claim that the algorithm learns the main patterns, for example, if these people are sick or these people are not sick. So in principle, they should go to different direction. But the main critique and the reason why deep learning things are cool, here it depends a lot on your n-dimensional space. Of course, it learns the shape of the data, which means the graph of connectivity. But it depends what is your dimension of your data. How do you represent your data? And this is the missing part. I think in SOM as well, you don't learn this thing, because you assume that your original dimensions, which is a me picture or this 2-dimensional data, or if it's about different measurements of different people and so on, it's fixed. So the idea is that is like orthogonal. You can do this topology data analysis for different kind of dimensions. So think about the combination of all of these possible dimensions. Each of them creates some kind of topological shape. For example, what I did recently, I hope I don't have internet. Oh. Yeah, okay. So, for example, in the case of these CT patterns, this is a combination of these convolutional autoencoders and SOM, and then topological data analysis, for example. The idea is that, for example, we take all of these points, and then these are the pictures. We train, don't think about it like a method, convolutional autoencoder, and then it gives me a 600-dimensional vector. So I cannot visualize any longer, but I know that this vector is talking about the similarity of the picture.
So you break
It's
it.
compressed.
You break it.
It's a compression.
To the point before the deconvolution somehow. This is where you get your vector.
Yes, exactly. You take the middle layer. Exactly. This is autoencoder. And then, for example, you can make queries, but these are unrelated, but I need to tell you. For example, if I now have a vector of this, it's not a picture any longer, but I just project the 600-dimensional vector, and it tells me this is the dimension. So I am sure somehow that this dimensionality, new dimensionality, is good. So in principle, you can create a SOM, as you have seen, I think, this one before. So this is similar to this digits. But then I was interested to know what is the shape of the data. For example, I said here is like more cities, and here is like more villages, and so on. But then you can implement this kind of topological data analysis on that, and it creates this kind of funny patterns. That, for example, these are very unique cities on this corner, and then the distance means that they are very dissimilar, and these are the main villages that you have this kind of circle. Maybe has a meaning in
Those are the
topology.
most common, no?
These are the most common actually, but these
And
are
what's
like
in the middle are the most
yes,
common.
because here it doesn't show the number of data points belonging to that area, but actually this is the middle, right? Bit from unicorns or unique cities to villages which are like no infrastructure, and then in the middle majority of the world is like that. And then here is the visualization of the color, for example. The reds are like here, maybe in Japan, they're very different, and the average of the world is like this pattern. And if here topology gives you this idea that, for example, what is the overall patterns, for example, as a graph, just as a graph. So you can think about it. Maybe there are some reasons for that. I don't know. I didn't discover further, but it's interesting that it's a kind of emergent, and then you expect that they are somehow similar, and then you have this linear pattern. And I think, I guess most likely this correlates with the density. And then here again you have another kind of distribution. You see that it's open, and these are the generic cities. These are interesting. These are not yet cities. These are like empty cities or very small villages. And here these are the generic cities because they are very similar. And this is again you have another distributions because the distances between these points are not the same as here. So these points are like very unique cities, and these are maybe the famous cities that we know. So this is one simple use of this, right? You can do it in many different applications, right? So what I tried to show you today in principle was a spectrum of applications that you can do with SOM, and I think because of that it's really interesting, because I don't know any other algorithm that you can do a lot of things like this with it. Like you take anything, you name it, it's just for one task. But here is like amazing. You can think about it in a very generic way. So there are some other ideas about like convergence of the algorithm. There are some mathematicians who are interested to know how this is working. There is no theoretical proof that SOM is finding the best indexing or not, but it's not a problem for computer science because it's very pragmatic. But nevertheless, people are interested in this. So I didn't show you how you can use this as a resampling application. I have done this for a company, and it's amazing. You can feel a lot of empty data with that, but you just need to think about SOM as a kind of data generator, for example, and you can think about SOM as a probabilistic machine as well, because these are all the probabilistic patterns. For example, if you talk about zeros, this tells you what are all the possible ones or zeros, for example, right? So, and within each of them, again, you have a lot of distributions. So it's like a way of encapsulating all of these possibilities. Whereas think about this comparing in comparison to linear regression, you try to reduce this. Here you keep them all here. So it's a kind of indexing, is not reducing your data set to a line. There is no line here. You can treat it like a line, but it's not a line. So it's a kind of, you can think about it like a cloud, right? Cloud of possibilities. And then just one simple visualization. I skip this part. In terms of what I told you, how this convergence work, you can think about each of these nodes of the SOM as a dynamical system. And then over this competition procedure, they should get stable, right? So we expect to get something like this. This is for the first data set that I showed you, this online training. They are fluctuating and then gradually get stable. And if I visualize only the first 400 values, you see that there are different patterns. So, but you can say that they're all converged. But you see some of them are different, have different patterns. Some of them just quickly converging, some of them takes time. And again, you can use SOM to study these environments. Now I have 100, the initial SOM that I trained for this data set was the first example, right? You remember this. This is the visualization of these points that you are showing here, right? You remember how they're fluctuating. What I now take is the differences between these two-dimensional vector over time. So if it's not changing, it means that it's getting converged. You can you cannot easily visualize 100. Again, here you have 40 by 40, so you have 1,600 points. You can train again with the sum to cluster these patterns of fluctuation. So if you do, instead of showing this, you can train it again with the sum of 20 by 20, and it categorizes it like this. That some of them are quickly converging, and some of them you see at the later states they have changed their positions. So, but again, this is a use for mathematicians maybe who are interested to see if you can study these patterns. And actually there are some works on this that they show each of these nodes are like a Markov chain, for example, over time. Because they are, you think about the state of these high dimensional vectors, over time they are moving from one state to another, and gradually in a Markov chain you get converged if you have a Markov chain, and then this is the final state is, I mean, this is the steady state of the Markov chain for each of the nodes. But it's not just independent Markov chain because they are affecting each other. So, but no, yeah, if you're interested, I know some people working on this. I can tell you some papers. So, yeah. I think that's enough for today. I think longer than usual. So if you have questions or comments, it might be confusing, but I tried to show you that there are a lot of possibilities with this sum. And I think as we continue later, for example, from this activation point of view, later when we go to this idea of deep learning, you will see that what is the shift, and you will see, I will talk about this idea of distributed memory. Here you don't have a distributed memory yet. Still you have this idea of centralized point. And I think here still you have, in my opinion, but it depends how do you represent it, you have this classical notion of the data, which is a ball. And this is like particle physics or classical physics, that you assume that your particles have a ball, right? You have this idealized space, and then you say this is my particle, and so on. And in terms of memory, in this and indexing as well, in these sums you have again still in the manifold learning principle you have this centralized notion of the space. What if you stack these layers of activations, you will see that the memory is not any longer in any of these points. So all of these points all together are contributing to just realize one point. So because of that is a different way of talking about the space. And I think it's because of that, for example, these deep learning methods are more powerful for more complex patterns. Yeah.